Hi everyone, my name is Amandine. I'm a PhD student in biomedical engineering at Polytechnique Montreal. Today I'm going to talk about impedance control in robotic rehabilitation, and more especially in control of exoskeletons, because it's part of my research project. So imagine that you want to control a robot, like a manipulator robot, and you want it to do some specific task, follow a specific path. How would you do? Probably you would, and most of the time you would implement a position or velocity control. So in other words, you would put a reference trajectory that the robot has to follow, and then the robot reach a goal. So now what if we add human or environment interactions? For instance, a collaborative work between the robot and the human, or more specifically with the use of an exoskeleton. So you cannot just put a reference trajectory to follow, because the robot could injure the user. So you need to add something else. A solution to that would be the force control. As comparison to classical controller, this controller would take into account the interaction forces between the robot and its environment, and that would prevent injuries. So here is a video of a comparison between a classical position controller and a force/impedance controller. So the impedance control is implemented on the left arm, and the position control is implemented on the right arm. And as you can see here, the left arm wouldn't go against the force applied by the human, but on the contrary, the right arm is just gonna reach its goal without taking into account the force applied by the human. So I spoke about force controller and impedance controller, but what is it? A quick definition would be that through impedance control, we would like to impose a desired dynamic behavior to the interaction between the robot and the environment. So if I come back to the notion of force control, it refers to both admittance control and impedance control. So impedance control is like a subcategory of force control. But when we talk about impedance control, we refer to mechanical impedance. And what is mechanical impedance? So you probably already know electrical impedance, which is the ratio of tension of a voltage to current. You have typical components like resistor or capacitors, and the impedance Z is linked to the resistive or capacitive coefficient. So it's a bit the same thing for mechanical impedance. So we can do an analogy between both of them. The mechanical impedance is the ratio of the force to the velocity. So there are three main components that we should know the impedance. The first one is the damper, the second one is the spring, and the last one is the mass system. So each impedance is linked to, respectively, the damper coefficient, the stiffness coefficient, and the mass. So why is it that important to know this specific component's impedance? So when you want to, for instance, control an exoskeleton, you need to control its actuators and their impedance. And in this way, to simulate the control, you need to model the system. And most of the time, an actuator is modeled by a generalized model of a spring, damper, and mass system, which can be translated by this equation. So now, when you think about exoskeletons, you can associate it to a mass spring damper system in interaction with a human system, also modeled in the same way, but with different parameters. So once you know how to model this system, you can now implement a control loop. So for the impedance control, this is an example of a classic way to implement an impedance controller. So you would find an outer loop for the impedance controller that takes in input the reference trajectory, and in output the command torque for the actuation system. And also you would find an inner loop that could be a torque, a position, or a velocity controller, because we want to monitor the behavior of the system through the process in terms of velocity, position, and torque. So for the impedance controller, or for the position, torque, or velocity controller, you can find different types of controllers, like proportional, proportional integral, proportional derivative, and proportional integral derivative controllers. So the choice of the controllers and the parameter tuning is based on different criteria, like the stability, the precision, the speed, and the robustness. So here is an example of a control loop of an exoskeleton named Lopez, which is an impedance controller. So you can find in the same way the block of the impedance controller that can take this form with different gain that you can model and try to fit with the desired impedance coefficient or behavior that you want to reach. And then you can see that there is a cascade of several controllers, like torque controller and velocity controller. So now when you look at this loop, you can see that there are several parameters to measure. So the first one would be the position. Then you need to measure some torques, the output torque, but also the torque at the output of the actuator, and then the velocity of the actuator. So for each parameter, you need several sensors. For the position, you need position sensor, like Hall effect sensor, potentiometer, or position encoder. For the output torque, you can use external torque sensor, like reaction or rotational torque sensor. For the torque at the output of the SCA, you can use Hall effect sensor, because most of the time the brushless motors have this kind of sensor integrated in their design. And finally, you need a velocity sensor, like a tachometer, a LCV, a piezoelectric sensor, or an accelerometer sensor. So now I wanted to show you an example of the implementation of an admittance control on the EduExo Pro of Oxibo. So the difference with the impedance control is that here you have to put in input a desired force, and the goal is to maintain this force constant. So as you can see on the video, when I'm moving my arm and applying a force on the forearm brace, the motor would follow my motion. And this is an example of a really simple admittance control given by the EduExo, the company. So here are my references, and thank you for your attention. Do you have any questions?